Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. I'm Sonia Olaoluwa and I'll be taking you through physics. Now we'll consider fundamentals of motion. In this topic, we'll be looking at the types of motion. We're looking at the concepts that have been taken note of in motion. We'll talk about relative motion, talk about parameters of motion. Graphs, we'll look a little into graphs of uniform and non-uniform motion. We'll also talk about the area under the graph of the velocity time. That's the velocity time graph. And also take note of motion under gravity, uniform circular motion, and causes of motion. The ultimate cause of motion is force. So let's go on. Types of motion. Oh, motion. Let's talk about motion generally. So what is motion? I know. Yes, you're thinking it. Motion is all about something moving from one point to another. The movement of one thing from one point to another simply talks about motion. So motion is simply, you can put that as movement. So what are the types of motion? Motion can be translational, it can be rotational, it can be oscillatory, and it can be random. Translinear or translational, that's motion between a place, one point and the other, where all that you have to pass through is a straight line. So, in other words, you can call it straight line motion or motions and straight lines. Those are what we call translational motions. We'll talk about rotational motion. Rotational motions about a point. Well, if you consider a motion, maybe people running in a football pitch. You run around the football pitch, that's a circular motion. So that's what we call a rotational motion. You end where you start from and you continue from there all over again. I'll talk about oscillatory motion. It's a to and fro motion. It is nearly rotational, but it is not any way rotational. It moves like a swing from one side to the other and you return. Also, random motion. Random motion is, simply put, a motion without direction. You just move anyhow. So any kind of any movement you just make, as long as it does not have a specific format or pattern or direction in which it moves, is described as random motion. So let's talk about concepts in motion. There are three major concepts. The three basic concepts we'll be talking about in motion today is the concepts of position and distance, also the concept of bearing and direction, as well as scalars and vectors. So, position, just the way you know it to be, the place in which a person stands, and distance. Of course, when you talk about position and distance, you're talking about us identifying things based on locations and the distance between those locations. So peradventure, we will have a graph sheet, talk about a position. Let's say one entity is at a position here. This position here is labeled X and is given the dimension of 2, 3. That's X and Y axis, location on your graph sheet. While the other position here, let's label this A so as not to avoid confusions, and we label this B is located at 4, 9. When we look at these two different positions, we see that there is a distance that has been created between them. That's why we talk about the concept of position and distance. So I stand in one place and my friend stands in another place. Then we can take measurement of the distance in between us based on our positions or our locations. So for us to take measurement of this kind of distance, we take note of the X, which are always the ones in front. It's always labeled X, Y, X, Y. So you take note of your X and you subtract one from the other. That is, in this case, 4x minus 4 minus 2 for our x axis it will be 4 minus 2, which will give us 2. So, if I want to take measurements of the distance between these 2 points, what do? The first thing I do is I take measurements across my x-axis. Now, my x-axis is indicating the distance between here and somewhere on this location here. So, that will be whatever I have here, that's x-axis. I have a 4 here, will be 4 minus, and on my x I have 2 here, which would give me 2. Then I also take note of my y-axis. Y-axis, I have 9. Take note, I pick first from B, so I must pick the next also from B. If I pick my x from from A, I must also pick my first x from my first y from A. You don't switch where you pick from. So, minus 3, and I have 6. Now, I don't just go and say, okay, the distance between both of them is 2 plus 6. No. Now, I want to call this my x value, and this my y value. The distance between both of them, I'll call it S, is given by x squared plus y squared, and then you find the square root of your answer. So, in this case, how do we go about it? Our x is 2 squared, our y is 6 squared, and then we'll find our square root. 2 squared is 4, 6 squared is 36, which gives the square root of 40. And square root of 40, when you use your calculator, that gives me 6.32, and that will be the distance between those 2 points. So that's basically what the concept of position and distance suggests. You can get the distance between 2 different positions following this formula. The concept of bearing and direction has to do with you using the description, or when you're giving the information of a particular location, just like we talked about position earlier. You're giving bearings of 2 different things or more, and you're asked to check up some other things. How people would move, a person moves from one place to another, and then moves through a distance of this, through that, of that. So when we take into consideration the bearing, it also gives us a sense that we can actually apply in solving many of our questions. Understanding of the concept of bearing, how we use bearing, would actually go a very long way to helping us in solving many questions when it comes to motion. Examples of such ways in which we can find its application is when we are trying to get which direction, and that is, we're considering the angles now. The angle at which a particular thing is going to move. When say something is projected at a particular angle, then we can use the concept of bearing, putting it together with the concept of, with the idea, knowledge of direction, merging it together to get our answers out. We cannot get to any location on the world without having a map. And your knowledge of how to handle the map, how to read your map, works a lot with the knowledge of bearing. When we talk about bearing, we talk about our current location or joining of positions in which we have been, in which the particular locations have been identified. Peradventure, you're being told a particular person is situated at a location 30 degrees north of east. Then you start drawing your cardinal points, your north, your east, your south, and your west. And then you measure from the north 30 degrees. And that shows us the direction in which the person is moving. Now, It shows us the direction in which the person is moving. Now, in the course of physics, in the course of working with on motion, we will come across different kinds of measurements or different kinds of descriptions. And on certain occasions, you're not given descriptions like something is 15 degrees north of east or something south of west or anything like that. You're just told a person rotates 213 degrees. And that you have to use your head to do the calculations. It's always advisable to always pen it out, draw it out and see what it would look like. So you have your north, your calculation, your measurement is always from your north through the east towards the south and to end in the west. So you move from here to here is 90, here to here is 180, here to here would be 270. But since we were given 213, so it will be somewhere in between here. And we can indicate it as 213 degrees. So basically, the concept of bearing and direction talks about us using geographical description of a place or location to calculate the movement or motion or distance and direction in which a particular thing is moving. Scalars and vectors. This is the third concept that we'll be reviewing as far as motion is concerned. What are scalars? Scalar quantities are quantities that you can measure their entirety by just taking note of their magnitude. That is, you consider their size, you can tell everything about them. Example of a scalar quantity, talk about your mass. Your mass here on Earth is the same mass you have if you're on the moon, in Jupiter, on Mars. Even when there is no gravitational pull, your mass remains the same. But the brother of mass is weight, which happens to be a vector quantity. Your weight on Earth is not the same weight you have on the moon. As a matter of fact, your weight on Earth is about 9 times what you would have when you are on the moon. This is due to the direction of the gravitational pull. The gravitational pull on the moon is not as strong as that on the Earth. So, it is not, vector quantities are defined partly by the magnitude of the quantity and also with the direction in which this magnitude is acting. For example, your force. You can apply a force of 10 newtons to push this body. And it would move effectively. But you need more force if you be pushing it from a direction as this. Because you are now pushing it downward and forward. And whatever force you are applying would be shared in both directions. So, that is vectors for you. You have to take note of both the direction in which the force is being applied or the quantity is being measured, and as well take note of the amount of quantity that is being applied. The difference between scalar quantities and vector quantities, when you take note of distance and displacement, or you take note of speed and velocity. I'll use distance and displacement. Displacement is the distance covered in between, the shortest distance between two positions. Now, if I should walk around a circle and get back to where I started from, my displacement will be 0 because the shortest distance between where I used to be and where I am. Since I'm at the same place, it means I have done nothing. I've moved no distance. I've moved no displacement. But the distance covered does not care about the direction. It simply cares about how much of movement have I done. So this is one of the major this is a major thing that distinguishes vectors from scalars. And very soon you'll be hearing us talking about speeds and we'll be talking about velocities. For the sake of simplicity, in physics we talk more about velocity this, velocity that. But in the reality, we don't work with velocity that much because how many of our rules are actually very straight, are actually perfectly straight. More of the time we'll do move in distances. So many other times when we want to take consideration, we take consideration of things in comparative with other things. And that brings us to the issue of relative motion. Relative motion is when you compare two different motions happening simultaneously and you take note of one to give you an estimate of the other. Peradventure, you have a situation of a person who is walking on the road and another person who is riding on a bicycle. The person moving on a bicycle will have a relatively higher velocity or speed compared to the person walking. And that's because he's using a cycling machine which actually moves faster. So when you want to consider the distance, you want to consider movements in relation of one particular thing to another, we do talk about relative motion. Relative motion is active in our world today. The fact that you seem to be standing in one place, you are actually in motion because the earth is actually spinning around the moon, spinning around its axis and around the sun. Which means the whole earth and the ground and everything is in motion, but we are still moving. So we have a relative motion in which, so in relative motion, basically what we try to do is this. Even though two things are moving at the same time, in our minds, we try to put one thing to stop, just the way in our eyes we see the earth as if it is in a stationary position while we are moving in it. So we put one thing to stop, we put one thing on a stationary position while the other thing moves. And usually the faster thing moves while the slower one stays in a stationary position. So for us to take relative motion about of what is happening between this person and this other man, man A and man B, we say man A on a bicycle is relatively faster than man B. Though man B is actually moving as well. But whenever we want to take the calculation of how much faster is he moving, let's say man A is moving with a speed of 2 meters per second and the one on the bicycle is moving with 5 meters per second. So what is the relative speed of man B to A? That will be 5 minus 2, because man A will have to look like he's on 0 for man B to look like he's moving his own. So the relative velocity here would be 5 minus 2, which will be 3 meters per second. Let's talk about parameters of motion. Parameters of motion. When we talk about when we mention of the word parameter, what comes to mind? Those things that fix together, that fuse together to give us what we are looking for. These are the items that are stated or unstated in our question. Most of the time when students look at parameters, they will say, write out your parameters. All we always think about is length, breadth, and that. Well, you're right to think about that. Parameters are those things that come together and are applied in a particular equation to get an answer or to resolve a problem, that is, develop a solution. So in motion, what are the basic parameters we do work with? We have to get familiar with the very terminologies as distance, which is the space between two positions, time, which is the duration between two occurrences, velocity, or let me come with speed before velocity, because I'll use speed to define velocity. The basic parameters we'll be working with in this section of motion are distance, time, speed or velocity, and acceleration. So let's take it one after the other. Distance, that talks about the space or the length between 2 points in time. It is usually indicated and represented with an S, and it is measured in meters. We have time, which is the duration between two occurrences. It is indicated by a t, and it is measured in seconds. We have speed. Speed is the rate of change of distance with time. Now, I use distance. Speed is a scalar quantity, and it has another entity, velocity, which share the same qualities as itself, but it is a vector quantity. So velocity is the rate of change of displacement with time. And what's the difference between displacement and distance? Displacement is distance in a specific direction, and it is always the shortest distance between 2 points. So velocity is actually the rate of change of the shortest distance with time. That is, the time taken, the rate at which the shortest distance between 2 points is being covered in the time, as in velocity is the shortest distance covered divided by time. So both speed and velocity are represented by the same entity. That's the same variable. That's v. And they both share the formula, the units, meters per seconds. Which is oftentimes represented as this or as this. Yes, meters is written as m and seconds is written as s. And lastly, but not the least, we have acceleration. Acceleration is the rate of change of velocity with time. That is velocity divided by time. So it is represented with meters per square seconds. Which is written as meters per square seconds, or as meters per hour. So these are the basic parameters that we do work with when it comes to motion. I haven't spoken about motion and its types. The following some questions will pop up on your screen now in a few seconds to see how much you understand what we've been talking about. Graphs. Graphs are graphical or descriptive explanations, that is, drawings that kind of try to explain certain things to us. So, when it comes to motion, of what use is a graph? I tell you, plenty of use. How is graph of use? Well, graph tells us what kind of motion we are experiencing, be it a uniform motion or a non-uniform motion. And it also tells us what is uniform in that particular motion. Let's take some examples. We have two types of graphs that we will look at. The first type we'll look at is what we call the distance time graph, and the second is known as the velocity time graph. But taking note of the distance time graph, there are certain things we need to take note of, very, very important, very, very key. These would be those things, those pointers to indicate, those indicators that will show us whether it is a uniform or a non-uniform motion. In a distance time graph represented S and T, when you have a straight line, it indicates uniform velocity. That is, the body is moving at a uniform velocity. Now, if this straight line should become wavy or curved, it shows it is ununiform or non-uniform. So, that's how we are able to detect from our velocity or our distance time graph. You might be wondering, why do we have to talk about graphs when we're talking about motion? But you'll see the importance as we go on. Graphs are actually descriptive descriptions, or should I use the word pictorial descriptions of what is happening around. Now, in our graph, we have two different types of graph we work with, and those are the distance time graph and the velocity time graph. The graph on the board shows the distance time graph. The distance is indicated with the S, and the time is indicated with the T. So, sorry, should be a small t. So, we have our ST graph. That's our distance time graph. Now, on our distance time graph, when we have a horizontal, a straight line, be it horizontal, be it slant, be it vertical, it shows uniformity, the kind of diagonal line. It shows uniform velocity. But when a line is wavy or curvy or bent somehow, it shows non-uniformity. In like manner, in our velocity time graph, it's slightly different from our distance time graph, because in velocity time graph, a lot of more information is being presented, such as our slanted line points at acceleration, which is uniform acceleration when it is straight, and our horizontal line talks about velocity. Up here, our horizontal line talks about distance. So, here our horizontal line talks about velocity, our slant line talks about acceleration. So our slants are acceleration, here our slants are velocity. So these are some pointers to take note of for now. Later in the course of this, we'll look into the others. Let's take a more excessive look at the velocity time graph. Let's take a deeper look at the velocity time graph, because that is what we'll be working with in most of our questions that we are likely to encounter in our examination. The velocity time graph, I have one on the board and showing my velocity to reach a velocity of 10 meters per second. A number of questions can come out of this. Questions like, what is the maximum acceleration? What is the maximum deceleration? What is the total distance traveled? What is the total time taken? And the likes. So, let's try to take the questions one after the other, and in this graph, we'll see how we can apply it. And also, we'll also consider what does the area beneath the lines of the graph of the velocity, beneath the lines of the velocity time graph, what does it indicate? The first question that I'm drawing out of this is, what is the acceleration required by this vehicle to travel from this point, from rest to 10 meters per second in 5 seconds? Of course, that's quite easy. All we need to do is to remember the formula for calculating acceleration. Acceleration is calculated as velocity divided by time. Velocity divided by time. So what is the velocity? That is 10 divided by, what is the time taken? 5 seconds. 10 meters per second divided by 5 seconds, which would give us 2 meters per second square. Another question that can be asked is, for how long did the vehicle move with a uniform velocity? It's a very interesting one, very simple one, but can be tricky. For how long did the vehicle move with a uniform velocity? The first thing to note is, when did the uniform velocity start? The uniform velocity is only indicated on the velocity time graph by an horizontal line. So what we need to look for is, where does our horizontal line start and at what time? So this is where our horizontal line starts, and the time is 5 seconds. Then the next thing to consider is, where does the horizontal line stop? Our horizontal line stops at this point, which is indicating 15 seconds. So how long would the vehicle move with a uniform velocity? That is between the time 5 seconds and 15 seconds. So uniform velocity can be found in 15 minus 5, which gives us 10 seconds. So the vehicle moves with a uniform velocity for 10 seconds. Also, a question can come up, with what deceleration or with what negative acceleration did the vehicle come to rest? Or how much deceleration was experienced when the brake was applied? We can calculate that in the final segment, because this is the one showing the vehicle coming from motion to rest, and it came to rest in between 15 and 18. Now we cannot use 18, neither can we use 15, because these are only pointers to the duration. What we need is the time duration, the time of the deceleration or the time of braking, not the time the brake was applied or the time the brakes or the time the car finally came to an end. So to calculate the deceleration, we can simply take note of our final velocity, which is the velocity of stopping, that is 0 here. We can term that as our V2, and can term this one up here as our V1. And also the time in this place, also we can call it T2, while the time at this place we call it T1. So taking note of that, our V here is 0, since it's stopping, minus our initial velocity, that's our V1, is 10. Our final T is 18, and our previous T is 15. So we have 10 minus 10 over 3, which will give us minus 3.33 meters per second square. Now, what does the area beneath the velocity time graph indicate? It indicates something very, very beautiful, and that is the total distance traveled. Yes, the total distance traveled by this vehicle in the entire time can be calculated simply by us calculating the area of this particular thing. And if we look at this particular shape, it looks like a trapezium. So I'll simply use the formula of a trapezium and get it out, and I'll also break it down into parts. Peradventure you come across a question where the formula of a trapezium can't work. You can break it down into different shapes, as one triangle, one rectangle, and another triangle. So let's see how we can go about the area beneath the graph. Earlier I said we can use the trapezium method, or you can simply break down the entire object, the entire image, that is the shape, into parts. So let's start with the trapezium method. What's the formula for calculating the area of a trapezium? The formula for calculating the area of a trapezium is given as half in bracket A plus B multiplied by H. While A and our B will be the horizontal lines, of course, since they are the ones parallel to each other. So in the case of this, we'll take our measurement from ear to ear. That's 15 minus 5 would give us 10. And from ear to ear is 18 minus 0, which gives us 18. So if this is our A and this our B, of course the height is the perpendicular height, which is given as 10 here. Then we'll go ahead and calculate. So our A becomes half 10 seconds plus 18 seconds multiplied by the height is 10 meters per second. This would give us 28 seconds multiplied by 10 meters per second gives us 14, and our area would be given as 140 meters per second multiplied by seconds. Now meters per second multiplied by seconds, the seconds will cancel out because this one is divided by second while this one is multiplied by second. So our A equals 140 meters. And like I said earlier, the area beneath the diagram, that is the area beneath the line, the curve on your velocity time graph, always show the total distance traveled. Let's see the second method where we actually split the shape into different parts. Now let's try the second method. In the second method, of course, this shape practically divides itself into 3 parts. And those 3 parts, let me label them P, Q, and R. P, Q, and R. P has the shape of a triangle, Q has the shape of a rectangle, and R has another triangular shape. So all we just need to do is calculate the area of each of the shapes, then add all of them together. When we add them together, it will give us the total distance traveled in the course of the movement. While this P will give us the total distance traveled during the acceleration period, that is between 0 and 5. Q will tell us the total distance traveled during uniform velocity period, that's between 5 seconds and 15 seconds. While R will give us the total distance traveled in the retardation process or during the time of deceleration, which is happening between 15 seconds and 18 seconds. So how do we go about this? Using the normal conventional formulas that you already know how to use to calculate each of these areas. That is, for triangle, area of P would be calculated using half base times height. In this case, my base is 5, my height is 10 as given. So I have half multiplied by 5 times 10, which would give me 25. Of course, when you insert the values that are involved, you have your 25 to be in meters, because this is meters per second and this is in seconds. The seconds will cancel out the per second. And the area for Q, of course, to calculate the area of a rectangle, it is simply length times breadth. So my length here is 15 minus 5, which gives me 10. And my breadth here is 0 minus 10, which also gives me 10. So I have 10 multiplied by 10, which gives me 100 meters. And lastly, area of R, of course, another triangle. So use the formula for triangle once again. Half base times height, which is half. In this case, my base is not 5 like here, it is 3. So I have my 3, and my height remains 10, which would give 15 meters. So the total distance traveled in the course of the movement is given by area of P in the course, total distance traveled in the course of the entire motion, that is the acceleration to the uniform motion to the deceleration, is area of P plus area of Q. Area of P is the acceleration, area of Q is the uniform velocity, plus area of R, which is the uniform deceleration, and it's given by 25 plus 100 plus 15, which would give 140 meters, just like what we got when we used the trapezium formula. So whichever method you find easier to use. On certain occasions, you can have your graph having more irregular shapes. On certain conditions, we may have graphs with irregular shapes, of course containing verticals, horizontals, and slant lines, forming a totally incomprehensible shape. Probably something like this. You have a uniform acceleration, uniform velocity, uniform acceleration, uniform deceleration, uniform velocity, and uniform deceleration. Such a shape like this, you can always simply break it down into as many parts as needed to make the work easier. As many parts as you need to break it down, you can always break it down so as to make it easier for yourself, for you to get your answer. Motion under gravity. On Earth, we do experience the gravitational pull, which is induced by the presence of many things. Actually, it's ranging from the moon near us, the rotation of the Earth, the revolution of the Earth, and virtually the reason why we can actually stand on one spot is because of the gravitational pull that is holding us down. I always tell people, or like they always say in the old adage, whatever goes up must surely come down. That's the work of gravity. So we cannot simply start calculating motion and will not consider the effect of the gravity on motion. Gravitational pull happens not with a uniform velocity, rather with a uniform acceleration, and it is represented with the symbol G. G is said to be of different values in different locations of the Earth due to the shape of the Earth. The Earth is not spherical in shape, rather it is like a sphere, but it is geode, and that means it has an oblong shape like that, more or less like an oval shape. So the center of the Earth is actually wider than when you measure the Earth about the center, that is horizontally, is actually wider than when you measure the Earth vertically. So that's one of the reasons why in different locations on the Earth, the gravitational force applied or acting on a person is different. And earlier I made mention of something about your weight on Earth being different from your weight on the moon. Yes, that is also another the effect of the field force of gravity. The gravitational pull on the Earth is placed at range between 10 meters per second, which is usually accepted generally, and about 9.81 meters per second. For the purpose of these classes, we'll be taking 10 because it is easier to work with. So let's come to 10. 9.81 also can actually be approximated to 10. In different places on the Earth, there are locations on the Earth where your weight, where acceleration due to gravity acting on you is an acceleration. There are different locations on the Earth where the acceleration due to gravity on you can be as low as 9.79, 9.73. That's around the polar regions. And at the equator, it can be as high as 10. But generally, the average was taken to be about 9.81. But for calculation purposes in senior school, secondary school, we do work with 10 meters per second. So, per second squared. Motion under gravity. When a body motion under gravity. When a body is actually falling, free fall from a particular location to the ground or from a particular height to the floor, it falls at a uniform acceleration and not with a uniform velocity. Also, we also need to take consideration of projectiles. Some objects are actually being propelled with an initial velocity. If an object is being thrown from the ground upward, vertically upward, it would go from the ground and to keep going. If there was no gravity, it would keep going until it would go to outer space. But due to gravitational force, it would get to a particular point in time, it would stop and start falling back to the ground. So, what are the formulas that we do use to calculate motion under gravity? All the formulas that we do use to calculate motion under gravity always involve acceleration. And there are about 3 formulas we have for that. And these are V equals U plus GT. We use G because our acceleration here is gravitational pull. V there represents the final velocity, that is the velocity of the particular object at that particular time that you are considering. The U there suggests the initial velocity, the velocity with which it was propelled at the beginning, or the velocity of the thing at the beginning of consideration. The G there points out the acceleration due to gravity, and T, of course, representing time difference between U and V. Yes, we also have plus or minus. Most of the time we come up with plus in most of our equations, but when we talk about gravitational forces, we put plus and minus because sometimes it is plus, sometimes it is minus. When is it plus? When is it minus? When you are throwing an object and it is going up, it works with a minus because you are moving in opposition to the pull of gravity. But when an object is falling, it comes with a plus because it is coming down with the support of the pull of gravity. So, if I should stand at the top of a mountain and I should throw this marker to the ground with a particular force, it would hit the floor faster than if I should just get to the top of the mountain and drop it. This is because I have increased my initial velocity. In like manner, if I should throw my marker up from the top of a mountain or from where I am right now, it will keep going, and to get to a point, it will stop and start dropping. Also, we have other formulas as when we talk about motion under gravity, we do not use S. Yes, we do not use S, we use H because it is the height that is affected by gravity. It is the height that is affected by gravitational pull. So, of course, all the other parameters there have been previously defined apart from the H, which represents height. And the third formula also being used H equals UT plus or minus half GT squared. All the formulas maintain their predefined definitions. These are the formulas that we do use when we have calculations involving motion under gravity. Okay, let's take this question. The question says a ball is thrown vertically up. It's thrown up vertically with a velocity of 40 meters per second. Calculate the maximum height reached. We're also required to find the time taken to reach that maximum height and the time it takes to get back to the ground. That is the total time of flight going up and down. So How do we go about it? We have to write out our parameters. What are the things that we know from the question? What information has been made available to us? The first thing we have here, which can be seen easily, is the initial velocity, which is u. The initial velocity with which the ball was fired. And that is given to us as 40 meters per second. The second thing which we know, but we're not told, but we know. Yeah, we know, even though we're not told. That is G. How do we know we need G? Because it is fired vertically upward. So when you fire something upward, the force that would act on it definitely is an acceleration force from gravity. So G, in our calculations, go with 10 meters per second square. Now, from our previously given formulas, we can now try to see what can we combine together to get what we need to find. Maximum height. If you recall what I told you earlier, when I throw a ball up, it will keep going and going, and to get to a particular point in time when it would reach its maximum height. And I made mention of something that most of you did not take note of. It will stop. So at maximum height, velocity equals 0. That is the final velocity. So for the question A, the first thing to note, our final velocity, which is v, equals 0 meters per second. Because it would actually stop. For it to, that's the indicator that it has reached the maximum height. So at that maximum height, when it stops, our v equals 0. And we can now put our h, which is what we are looking for. We don't know what our h is. So from the formulas pre-listed, which of them solves this question? So here are our three formulas, earlier stated. We have our first formula, which has V, U, G, and T. The problem with this formula is our parameters does not involve T. So here, it doesn't fit. If we also consider the last formula also, T is coming up. So we'll be having two unknowns. Doesn't fit. That leaves us with the middle one, which has V. We have our V. It has U. We have our U. It has G. We have our G. And our unknown is H. So that's the appropriate formula to use. After selecting your appropriate formula, you start putting in your parameters into the formula. So let me write out the formula so we can start work. That's v squared equals u squared. Yes. Will it be plus or minus? Since our object is being thrown up at this particular time, so it should be minus because we are moving in opposition to gravity. So we'll have minus and not plus 2gh. So our v squared equals 0. Our u is 40 squared minus 2 into bracket 10 multiplied by h. Well, you can take the whole expression to the other side, so we can just solve out. So we have 20h would be equals to 40 squared is 100 and 1,600, and dividing through by 20, our h equals 80 meters. All right, the second question asks the time taken to reach the maximum height. the time taken to reach the maximum height. Let's bear in mind we still have our given parameters are the initial velocity with which it was projected and our acceleration due to gravity. So we're still pointing to that maximum height. Well, there are two ways we can go about it. You can choose a formula that already has an h since we have calculated our h, but I always like to not work with answers I calculated. I always like to work with what I have already. So I'll choose to work with another formula which has something that has already been given to us. That is, at maximum height, what is the condition for the maximum height? At maximum height, velocity, maximum and final velocity, that's v, would equal 0. Let's also bear that in mind. So that particular parameter becomes useful once again. V equals 0. And what are we looking for this time around? Time. Let me call it time h. Is unknown. I call it th. So, which formula contains all of these parameters? This time around it comes a bit easier. Our very first formula. It has v, it has the u, it has g, and it also has t. The other ones would have other things that we do not want to work with. So we simply import our formula out. That's v equals u. Again, we are still going in opposition to gravity, so it means minus gt. So as usual, we pick out our parameters. Our v is 0, our u is 40, the minus, our g is 10, while t is t. Moving it to the other side, that's 10t equals 40. Divide by 10, divide by 10. T equals 4 seconds. So with that kind of proportion, that's with the force, that's the velocity with which it was being thrown, in 4 seconds, the ball should reach the maximum height. Having calculated the time it takes the ball to reach the maximum height as 4 seconds, we'll proceed to calculating the time it will take the ball to return to the ground. So you can see that I've taken out all my previous parameters. Yes, I did that on purpose because those parameters do not really apply now. Our ball has been thrown up and our ball has gotten to that point where it stops. So calculating the time it's going to take the ball to get to the ground is going to start from where the ball actually stops at. So the new set of parameters to work with are those things we have actually calculated before now, or one of them. So let's start with the first one, which will be our initial velocity. Our initial velocity at the point where the ball starts to fall is 0, because it will be falling from rest. That's 0 meters per second, since our ball is falling from rest. Now the second thing also to note is the height. We have calculated the height, that is, so we know how far above the ball is falling from, and our height was calculated as 80 meters in the first question which we handled. And the third thing to note is the acceleration due to gravity. That's the gravitational acceleration. That's g, which we have always noted to be 10 meters per second squared. So what are we trying to get? Time. The time it will take the ball to strike back. That's our unknown. How do we go about it? So we'll go back to our formulas and we see which of these formulas accommodate all of these parameters. Our first formula can't go because it contains a v and we don't have a v here. Same thing applies to the second formula, presence of v, which is absent amongst our parameters. our third formula looks good to go. So we'll pick it for this particular question. So I'll write it out. H equals UT. Now, in previous questions, we have been using minus among all our options. But this time around, we would not be using minus because our motion is now in support of gravity. So we'll be working with plus. Our previous two questions, our motion were in opposition to gravity. We're going up. But this time around, we are coming down, which means we are coming in support of gravity. So we have plus half gt squared. So, of course, we can do a little trick trying to bring together what should be in front and what not should be in front, but don't worry your head about that too much. Just substitute your values and let's work it out. So substituting values, our h is 80, our u is 0 multiplied by t, that will definitely give us a 0, plus half times 10 times t squared. By default, 0 times t gives us 0, and by default, half of 10 is 5, so we have 80 equals 5t squared. You can divide through by 5, and t squared will be given us 16. So our t would be the square root of 16, which is 4 seconds. Yeah, I expected that. And do you know why? Because normally, the time it takes the ball to move from the ground up is the same time it will take the ball to come back down, except an external force is applied when it gets to the top. So, this is how long it will take the ball to return to the ground. But if you talk about the total time of flight, let me call it here. If you talk about the total time of flight, then it will mean the time it takes the ball to move from the floor to the top and from the top back to the ground. Total time of flight is usually taken as capital T, which is always equals to T to reach maximum height and plus T to return. Usually, T to reach maximum height, which is TH is usually equal to T to return, which is TR. So usually it's capital T is usually equals to 2 times TH. That's about everything we have to talk about on motion under gravity. We need to understand how things move and the concepts behind motions in circles, especially since most of our devices are designed in circular operations, especially our mechanical devices. Our fans, our cars, they all bring about the need for us to understand how things work in circles. And remember the other time I was saying something about velocity and speed, and I told you that we have speed, and speed is either it considers whether circular or not, but velocity, once it's circular, it is irrelevant. That's true, but I'm also about to introduce you to something called angular velocity, which is velocity in circular paths. So it is actually possible for there to be a velocity in a circular path. It is actually possible for there to be a velocity in circular paths. How does this occur? When we have an object moving in a circle, at each point in time, the object tries to escape from the circle with a force or acceleration or velocity, depending on how fast it is moving. It will try to escape from the circle in a tangent, in a line that is tangential to the circle. That is a line that is at 90 degrees to the radius of the circle. Now, at that point, the velocity kicks in. There are two types of this velocity. We have the centripetal and the centrifugal. While the centripetal velocity tries to pull everything towards the center, the centrifugal tries to push everything away from the center. So they are like brothers and sisters. And that's the way to keep the balance. Once there is a balance between both of them, the object would keep moving within the circular part. Now, if the centripetal should get higher than the centrifugal, the object would collapse towards the center of the object, of the circular part. And if the centrifugal should get higher than the centripetal, it would go off the path and fly away. So, at this point, we'll come to talk about centripetal acceleration and centrifugal acceleration. There is something usually said for a rocket to actually escape for a particular body to escape the atmosphere, it has to move with a particular acceleration or velocity, acceleration and velocity, which is greater than the centripetal force of the Earth. That is an acceleration which is much, much greater than the gravitational pull of the Earth. So, that's about all we'll talk about for now in relation to centripetal and centrifugal acceleration. Cause of motion. Well, Sir Isaac Newton came up with a very interesting law. He said that a body will remain in its constant state of motion or will stop moving. That is, just mean in states of rest, unless an external body acts on it. So, naturally, a moving body should keep moving and a non-moving body should remain stationary. So, what actually can make a thing that is not moving to move or make a thing that is moving to stop? That's why we'll talk about the word force. You see, force is that external push or pull which you apply on the body. And your force is always with a direction. It's a vector quantity. It acts based on the direction in which it is applied. Force is calculated, F is calculated as mass multiplied by acceleration. So, our force can actually turn acceleration, which your body initially has, to nothing, and it can actually give your body, which has no velocity, a velocity by giving it a form of acceleration. So, ultimately, nothing can cause a body to go into motion or stop being in motion unless there is a force. In summary, in this topic, we've considered the fundamentals of motion, and we've looked at types of motion. We mentioned 4 types of motion: translational motion, random motion, circular motion, and oscillatory motion. We talked about concepts in motion. We talked about the distance, position, distance concepts, where we can calculate position. You can use position of a place, of people or things, to calculate the distance between them. We talked about the bearing direction motion, where we take into consideration bearing and angles. We talked about the scalar and vector quantities, the scalars and vectors, and then we talked about vectors and scalars being entities that can't be described completely using their magnitudes only, and vectors are quantities we need both magnitude and direction to quantify. We also moved on to talk about relative motion in which two bodies moving, we have to put one to a stop in our mind for the other one to move, and we can compare how one is moving in relative to the other. We also talked about the parameters of motion. In parameters of motion, we defined each of the parameters as distance, as a length between 2 points. We discussed time as the duration between two events. We also discussed speed and velocity, that they have the same formula, of course, and one is vector, one is scalar, but it is simply rate of change of distance with time. And we discussed acceleration as rate of change of velocity or speed with time. We looked at the graphs, and we talked about in this distance time graph, we say an horizontal line means constant distance, and a slanted line indicates that it is a constant velocity in the distance time graph. But in the velocity time graph, a slanted line indicates uniform acceleration, while an horizontal line indicates uniform velocity. We also mentioned that the area formed beneath a velocity time graph line is the total distance traveled in the course of the time stipulated. We also went ahead to look into motion under gravity, where we talked about the formulas, and we said these formulas also that we can use for straight line motions also apply under gravity, only that acceleration, when we talk about gravity, is acceleration due to gravity. That is, acceleration when we consider vertical motions is always g, which is 10 meters per second, or 9.8 meters per second, or 9.81 meters per second squared, as appropriately as stipulated in your exam question. We looked at uniform circular motion, where we talked about centrifugal and centripetal forces, centrifugal acceleration, or centrifugal and centripetal velocity. The ones that keep in are the centripetal, while the ones that keep out are the centrifugal, whether velocity, acceleration, or force. And finally, we talked about the cause of motion, which is force. Without an external force, a body will remain in its constant speed or in its constant state of rest, according to Sir Isaac Newton. I hope you understand the concepts which have been discussed. If there is any you don't understand, you can go over the video once again. Questions will pop up on your screen in a few seconds. Try to handle them. I believe you should be able to take care of them. Thank you.